So a couple things. I haven't followed up with the pre-stress plant yet. I'll do that today, just kind of because I'd like to again set a timeline of when we should have these things designed by. So we're gonna have so you handed in another homework. I still have only graded one homework. So this week I'm gonna try to get the next maybe two of them graded. Right, that would be the previous one, and then the one you just started. You have another homework coming up. This is shear design one that you're working on right now. Then we do one on deflections, and we do one on pre-stress losses. I think that, and so we just have two more homeworks really. And so that really what we're going to discuss, topics we have left to discuss, is deflections, which we're going to talk about today, and pre-stress losses, and then composite members. So what if you have pre-stress deck, a pre-stressed beams, and you put onto it a composite regular concrete deck, which is a very common thing to do in highway design and stuff. You would put down some pre-stressed things and you put on a deck on top of it for a riding surface or driving surface. Or in a floor design, if you have that, you put on a topping slab on that just for wear and tear and stuff like that. And so how do those things behave compositely? And then we'll have an exam. So sometime, usually in the past I looked, it's right around Halloween is when we have the exam, right? Somewhere in there we got to slip in post-tension floor design stuff. I don't know if that'll be after the exam or before the exam. I haven't worked that out yet. Part of the problem is the guy, Kyle Boyd, who's going to help me with is non-responsive. He's ghosting me. He sent me hats. This is his hat. He started his own company. Recently, and I think that's what the problem is he's busy, I think is what the problem is. And you guys aren't taking priority. So, but I got to work out that too.
Probably because you didn't share a bed with him.
It's probably, yeah, I didn't sleep with him. Okay. So then, let's talk deflection. So we just finished shear design. You're in the middle of it. Hopefully you've started it and are in the grips of what to do. We spent a lot of time last week on some of these variables that people have messed up in the past. I gave you what the solution's supposed to look like, and just stop the positive, negative guessing stuff you've been doing. He's like, well, that didn't work. Let me just independently change all these things to negatives or positives and see if I can find a combination that works. It works out eventually. But we learned there was reasons.
Yeah, why it did.
There was reasons why it wasn't working out and why it was working, and because you weren't trusting the solution or the process, right? So. Anybody tried the homework yet? Okay. Yeah, so it's a fun day. It's not due till Friday. Yeah. Good point. Yeah, so weekends are for. The weekends are for studying and doing shear design and pre-stress memory. And so again, idea behind these things, each one of those methods because it all varies along the length. In Excel, if you want to do it in Excel, right? You have your location along the thing. You can trust the mirror if you want. You could just do half. That's what I did in my solution. I just did the first half of it, the first half of the span, because it's going to be mirrored after that. But you just have, what one equation is at every location, what the other equation is at every location, what the other equation is at every location, and then another column that's the minimum of those three, right? That grabs those things as it goes along. And then you're going to do that and then keep doing that for the other method. You're going to, same thing. It's going to vary because depending on where you're at, different equations are going to control in different locations. And you should see that where it's failing someplace in between the middle and the end, and for the reasons why we discussed it. Okay, so now let's talk about deflections. Deflections are very difficult in pre-stress members. Right? First of all, it's concrete. Concrete's very hard. Everything's hard in concrete. Right? Everything's difficult in concrete. Welcome, guys. Neil is a blowout, dude.
It's always fun to see that.
It is fun to see. That's the games I like to watch. There's no anxiety driven at all, right? It's just oh, look, it was great. What's that? No, that's the scary part. It was the scary part. It was cool to watch. I didn't think, Neil, I didn't have any faith in this, and
Last time I get you tickets.
yeah, it was, right, because Eastern Washington, they only lost to Washington State by 3 points with a last-minute field goal, right? So I was like, oh, they're going to be real good. And then we had trouble with Mercyhurst, And so I was like, oh God, what's going to happen? But then it was awesome. It was cool. I like games like that. Tell everybody to keep it up. Keep blowing them away.
I thought the Eagles were going to lose it.
You do. The Philadelphia Eagles? I think they're going to lose it every time. Because that's how I am. But then
Baker won his first 3 games in the last minute, and he had the chance.
he had a chance. He blew it.
He's a moron. Fantasy quarterback.
Okay. So it's very difficult to calculate these things, right? And we'll talk about why, right? I mean, one, it's concrete, right? So, and difficulties. All right, why is it difficult, right? Let's write down something. P.S. Pros tension members are typically slender, right? Because that's the point of it. We're trying to reduce our cross sections, make them very thin, okay? Therefore, deflections are high. And can be an issue. Therefore, important to get accurate estimate. But that is super hard. It's super hard to do, right? Because it's concrete. And we'll look at it a little bit. I mean, they have when you talk about ACI 318, ACI 318 is a committee. There's a committee amongst all the ACI people. That's 318. There's a full committee in ACI that's associated with deflections in concrete. It's ACI 435, and they have a huge document that's associated with this topic. Okay, I'm getting ahead of myself, but it's very hard to do, and we'll get there. Pre-stressing. Let's talk about why it's difficult. Causes upward deflections. As gravity causes downward deflections. Right? So you got a couple different things going on. Uh-oh. My sentiments exactly. That was it, right? And this is obviously for simply supported. Things get even more complicated. I mean, only simply supported, it already is complicated, right? If you add in the fact that things are not necessarily simply supported, then things get even crazier. It keeps doing this. It keeps like bogging down in this text. It's slowing me down. I should listen to Ernie and not update immediately. So there's a couple different things fighting each other in there. Have to get creative, we'll see this a little bit later today, to account for deflections and with pre-stressing. Right. Our methods, even if we were considering everything to be elastic, right? We're all set up. Everything we've talked about deflections before is that those are your mechanics of advanced mechanics right now, right? That fourth order differential equation governing beam bending, EIU prime is equal to negative W of X. That's for externally applied loads. What the hell do we do with an internally applied load? How do we account for that, right? We've never discussed that before. How do we account for this internally applied loads, and how do we make this work? And so there is a way that we do this, and it's we pretend that the internal loads are actually external loads, and then we use our solutions for external loads. And that's what I mean by getting creative. But we'll discuss that more in a second. We'll write each one of these things down. We got cracked versus uncracked. And right, because some of even in pre-stressing, you're allowed to let your beam crack. You can do that. We're trying not to do that, right? That's one of the reasons why we're doing pre-stressing, is to prevent cracking from happening. But if for some reason you have cracking, you can calculate deflections. But we're going to focus on uncracked in this class, right? Right, and this just for those of you taking advanced concrete, right? We're going to use IG, ICR is one that used in, or IE. Those of you who took regular concrete, you remember this? You did like, oh, it cracks, and then since it's cracked, let's assume that it has a reduced moment of inertia as being I cracked or IE, depending on which method you use. We're not going to do that. That is valid in here, okay? But remember, again, one of the main reasons we're doing this is to prevent our beam or our sections from cracking. Right? That's the whole point of pre-stressing. We talked before, we ran into this once before when we were talking about classifications of beams. There was U and there was T and there was cracked. And we said, we're gonna focus up here on the U part. We're gonna focus on the U part. That's what it would define in there during that definition, is where it would tell you how to calculate deflections. If you're in U, it says calculate deflections, like we're gonna talk about right now. If you're in one of the others, the T or the C, if you've classified your beam as C or T, then you would use IG or IE depending on what method you are. Because it gets weird too, right? Because even if you decide, and this happened in regular concrete, I'm sure Tim talked about it, is when you say your section is cracked and you calculate deflections on cracked, you assume the same I along the entire length of the member, but that's not necessarily true, because in the middle it may be cracked, but near the ends it isn't cracked, but you're assuming that it has a cracked section modulus over the whole length. Just in case you didn't know that, that's part of the solution. So it gets really weird. You just start guessing. This is concrete, unfortunately. There's a lot of guessing that happens as you go along, right? It's weird, but we're gonna try to put some logic behind some of this stuff, all right? You can have nonlinear behavior too. Material behavior. That's something that makes things difficult. Although deflections are considered at service loads when we assume materials are linear elastic. And we're going to make that assumption. I mean, but really, if you're really calculating deflections and really cared about them over the entire lifespan of the structure, you'd have to take into consideration nonlinear material behavior. But we're just going to stay in the elastic range, where everything stays linear. Okay. The other thing floating around is long-term deflections. Oh, God damn it. Crashed on me. Ernie's right. Long-term deflection, because creep is in there, right? Creep is always floating around as a topic here. How complicated this gets, right? Is the concrete's going to creep, right? And so the gravity concrete, right? It's going to creep down, right? Pre-stressing, it's going to cause it to creep up. We talked about where that C is at, where your compression force is at. If that net compression force is above the neutral axis, it's going to creep down. If the compression force is below the neutral axis, it's going to creep up, which is really weird, right? So not only is that creep causing like the deflections to happen, it's also causing your pre-stress losses, or causing your pre-stressing to reduce as you go along, right? The concrete shrinks, your steel is stretched less, so your pre-stressing forces go down. They're going to change as you go along, right? So you have multiple things that are happening, and we're trying to account for all that. Despite all this stuff up above, you also have to account for the fact that over time, things are going to creep around. They're going to creep up, they're going to creep down, there's shrinkage that's happening, you get pre-stress losses, and all those things are intermingled, and how the hell do you deal with that stuff? And nobody really knows. That's the answer. Nobody knows, and we're just going to guess. Right? And then you'll see what ACI says, and that's basically what ACI says. Hey, you need to account for this. We don't know how, but you should do this. You should make sure you do this. It literally says that. Well, word for word, it says that. Right? Under creep, let's talk about under creep. A couple of those.
No, those words.
Those words exactly. Right? Creep causes deflections under sustained loads. Up versus down, dependent on location of resultant compression force as discussed in C-line method. Right? We talked about that in the C-line method, right? And we got a little distracted during that time. But we talked about that, right? If it's above, it creeps down. If it's below, it creeps up, right? But that's happening through all this stuff, right? Creep causes pre-stress losses. Which affect deflections. They're all tied together. Shrinkage always causes downward deflections. Right? Shrinkage is another thing. That's just when concrete cures, it also its volume decreases, it shrinks down, and then that will cause obviously pre-stress losses. Also, that'll always cause a downward deflection because it shrinks everywhere. Okay. You get the point. It's very complicated for long-term deflections. All right, so this is actually 318.19 that I got here. 19 is the code sections that I have in there. Okay, they provide general guidance. They prescribe what to use as a moment of inertia, and it sets the limits, but it leaves a lot to design, right? The engineering judgment. I think Tim stresses this a lot in his design classes. It's like ACI leaves a lot to you guys, right? It's like, what do you do? Well, here's some guidance. It's up to you. You decide what to do. Okay, so let's see what it specifically says in terms of these components. Okay, so this is chapter 24 is where it initially defines these things. It says deflections due to surface gravity loads should be good. This chapter shall apply to members design minimum serviceability, including A through D, which is deflections due to surface gravity loads. Okay. Oh, she froze on me again. There we go. Members subjected to flexure shall be designed with adequate stiffness to limit deflections or deformations that adversely affect the strength and serviceability of a structure. So it's saying, hey, you should really take this into consideration. So it says you need to calculate deflections. Okay. So this says, and it says over here in the commentary, this section is concerned only with the deflections or deformations that may occur at service level loads. When time-dependent deflections are calculated, only the dead load and those portions under or other loads that are sustained loads need be considered. Okay, so it tells you. So again, some guidance. We're going to do service loads. We don't have to worry about ultimate loads. Ultimate loads have to do with when people die. People don't die when you violate deflection requirements, so you don't factor your loads. For non-pre-stressed members that do not meet the minimum thickness requirements for non-pre-stressed members that support are attached to non-structural elements, like I'm trying to get the point. And for pre-stressed flexural members, deflections are required to be calculated by 24.2.3 through 24.2.5. Calculated deflections are limited to table 24.2.2. So in regular reinforced concrete, you don't have to calculate deflections, right? I think you did, right, in Tim's concrete class. You did calculate those deflections, but you don't have to because you could just meet those H minimum requirements. So those of you that have only done structures 2, William, Noah, you undergrad people, if you've only done structures 2, there was an H minimum, right? That H minimum. As long as you meet those H minimum requirements, you don't have to calculate deflections, right? Pre-stressing, you always have to calculate deflections, and you have to calculate those deflections and compare them to the limits in 24.2.2, okay? Another little side note, I have a friend of mine that I went to grad school with, and he started a company that does structural forensics, and he comes and he goes to all these ACI committee meetings and ACI conferences, and he discusses all these problems. And he always focuses, he does structural forensics, so if something fails, if something doesn't work the way it's supposed to, and you're the owner, and you're like, this sucks, like I didn't want my building to fail, I didn't want it to leak, so you hire a company to come in and do a structural analysis and figure out what went wrong. And then the other side hires a firm as well, and then you fight each other and see, what went wrong, right? And so he always goes to these concrete meetings. And I was like, well, do you ever go to the steel ones? He goes, no, because nothing ever goes wrong with steel. So it's always concrete. It's always concrete, right? But he said most of the cases are associated with serviceability cases. Obviously, failures are a big thing, right? He's been involved in some of these. In Tim's concrete class, you guys talked about that apartment that failed. Remember the apartment complex that failed in Florida? Didn't you do that?
Yeah.
Right? Did you?
The one that was a few years ago.
Yeah, a few years ago, and the thing, there was like a water leak, and it washed something out, and then it collapsed. Do you remember this? I think it was like a case study. Dylan's company was involved with that. Anyways, it was concrete. Most of the cases, though, are associated with deflections. They get excessive deflections. Like he has an example, one case, like in an emergency room, like they go inside of it was an emergency room. They go into this, it's like on the second floor or something like that, and all the equipment would like slide to the middle because the deflections were so big, right? But the whole point of this is, he said he's never had a case where they had deflection issues when it has met the H minimum requirements. So if you just that's as designers, as you move forward, always just compare it to that H minimum. As long as you meet that H minimum, you're probably going to be okay. Most likely going to be okay with your deflections. It's when you get fancy with them. But in pre-stressing, there is no such thing as an H minimum, so we have to calculate deflections, which means we keep Dylan employed. Okay, because we're not going to be able to do it. So here's the limits. So it says you have to calculate deflections. So right here it says you have to calculate deflections. In this section, you have to compare them to 24.2.2. And oh, by the way, use service loads. Okay, so here's 24.2.2, and this is the limits. Right? So it's very prescriptive, right? Are we dealing with flat roof floors or roofs and floors, right? Do you meet these requirements? And oh, by the way, they end up over here, right? And so this is the L over, you've seen these before in ASC, like L over 240 or L over 360 or L over 480. That's where your limits are at, right? So you're going to calculate your deflections with one of the methods we're going to get into, and then depending on how those deflections are, you can compare them back to here, right? And see if you meet these deflection requirements. Right? That's what you're comparing them versus. Okay, so they break it up into immediate deflections and long-term deflections. So we're going to calculate the immediate deflections. Right? So it says right here, immediate deflections shall be calculated using the methods or formulas for elastic deflections, considering effects of cracking and reinforcement on member stiffness. Okay, so it says it just says use a method. It doesn't tell you how to do it, but just says use elastic analysis, so that EIU prime equal negative W of X, that's the elastic analysis, or they're bending. What you can calculate deflections with VA. VA, or like structural analysis program, will calculate deflections. There's all sorts of ways to do it because they all are based off of elastic analysis. So it says do that, okay? For calculations of immediate deflections of uncracked, and we're going to stay in the uncracked area. For calculating immediate deflections of uncracked prismatic members, the usual methods or formulas for elastic deflections may be used with a constant ECIG. EC is the modulus of elasticity of the concrete. And anybody know the equation for that? Normal weight concrete. So you got to be part of the brotherhood or sisterhood, right? Or otherhood. Yes.
57,000 square.
You're damn right, Anika. Damn right, nerd. Right? Freaky. Oh, what a nerd. You're part of it. You're part of the hood. Oh, yeah, that's what side. The hood. You're part of the hood. Right? 57,000 square root F prime C. That's exactly right. Good job, Anika. As for normal weight concrete, there's another one. There's another equation that's a little bit longer that has like the weight to the 1.5 or something like that. That's what you use, but it ends up being 57,000 squared F prime C. So that's what the EC is, and then IG is your gross moment of inertia, right? So you would just calculate the moment of inertia for your section, and then you just use the gross moment of inertia. We're not using cracked sections, right? And then you get to assume it's along the entire length. Right? However, if the member is expected to crack at one or more sections, or if its depth varies along the span, a more rigorous calculation becomes necessary. But we're going to stay away from that because it's already hard enough as it is. Okay? And here's some of that stuff that I was talking about before. What IE is, the effective moment. This is tied to just a little. I'm not going to do it, but just to show you what it's doing. Instead of like if your real moment deflection or if your real moment is a moment versus curvature is what it is. And then this is the slope. Just to refresh kind of those of you seen it before. This is EIG before. And say if you're trying to calculate the deflections out here, what it does is just kind of cuts the corner off. Oh, I didn't want to make a triangle. Now it's making fucking triangles. I wanted to make triangles before. I'll stop early. Okay. It cuts that corner off and calls this EI effective. So it just kind of cuts that. It's like I know it's going to go up and then it's going to go that direction. So one of the ways you just cut across the corner. And it's again, just an estimate, but it's supposed to take into consideration the crack section. Right? Or you could do one, you do one, I think with the cracked moment, you calculate like the deflection up till cracking, and then you calculate like the reduced stiffness of the cracked load, and you actually add the two together. You do the deflection calculation twice, one up to where it cracked, and then another one with this would be I cracked right here. I cracked. There's two different ways to do it. But anyways, we're not getting in there. But that's where this is at. And it's the same section that you saw it in your other concrete class. But we're just going to look at deflections that are going to be happening kind of in this elastic range before things crack. Okay. So where we come down, there was some more stuff valid to this. Right? And that's why it's all spread out. It's because it has the regular reinforced concrete stuff mixed within it. So I said before, I'd like to see the pre-stressing stuff kind of on its own someplace, okay? For pre-stress class U, the uncracked sections, beams is defined by 24, it shall be permitted to use the IG, right? We already said that once before, okay? And this is where I say for pre-stress class C and T, we're not going to do this, but this is where it defines what you do with class C and T using the crack section properties and stuff like that. So again, just reiterating, Class U pre-stressed concrete members may be calculated by usual methods or by formulas for elastic deflections using the moment of inertia of gross uncracked sections. So keep saying the same stuff over and over. We're not going to do this stuff. Okay. Calculation of time-dependent deflections. Okay, so we're getting into time-dependent deflection. So all the stuff up above, it doesn't tell you, right? We haven't talked yet. It doesn't say how do you account for the pre-stressing. It says use normal methods, but it doesn't say anything about what you do about the pre-stressing deflections because they're internal to the system. They didn't tell us what to do with that, so we have to come up with our own method, right? For calculating long-term deflections, so that's the end of the immediate deflections. So you calculate immediate deflections, but then time-dependent. What do we do about time-dependent? And so it says, right, calculation of time-dependent deflections. So non-pre-stress members, I think you did this in concrete class. right? With a little XC floating around. Didn't you do this, right? Yeah, he calculated. It very specifically tells you this is how you calculate long-term deflections, right? For non-pre-stress members. You're like, oh, great. It has this nice method. It tells you all these values, very prescriptive. And this is what it says for pre-stress members. For pre-stress members, additional time-dependent deflections of pre-stressed concrete members shall be calculated considering stresses in concrete and reinforcement under sustained loads and the effects of creep and shrinkage of concrete and relaxation of pre-stress reinforcement. That's it. That's it. That's all. That's the only guidance it gives you. Look, that's it, right? If you scroll down, it jumps down to composite members, right there. But it doesn't say. That's it. That's all it tells you. It's up to you. Go figure it out. Just guess. Guess what it's gonna be, right? I mean, it does give you a little bit of guidance. I'll show you over here. I mean, in the commentary is where it gives you the guidance. Oh. This commentary. Okay. I'll just read it to you. Calculation of time-dependent deflections of pre-stressed concrete flexure members is challenging. The calculations should consider not only the increased deflections due to flexural stresses, but also the additional time-dependent deflections resulting from time-dependent shortening of flexural members, right? Because that's going to affect my pre-stress losses. That's going to affect just the movement in general, right? Pre-stressed concrete members shorten more with time than similar non-pre-stressed members due to the pre-compression that the slab or beam, which causes creep. So basically all that compression that's included in there, concrete creeps with that compression, it causes it to creep and deflect and shorten, right? This creep together, along with shrinkage, results in significant shortening of the flexural members that continues for several years after construction and should be considered in the design. The shortening tends to reduce the tension in the pre-stress reinforcement, reducing the pre-compression in the member and therefore causing increased time-dependent deflection. So it's this circular thing that's happening. It deflects more, which means because of creep, and then your pre-stresses get it less, which means it deflects more. And so it's just like this, they're all tied together. Okay. Another factor that can influence time-dependent deflections of pre-stressed flexure members is adjacent concrete or masonry that is non-pre-stressed in the direction of the pre-stressed member. This can be a slab of pre-stressed slabs and shrinkage. They can be pre-stressed members tend to shrink. Right? So it just keeps going on, saying this is really hard. Okay. And then it does give you it does point you in some certain directions. It says any suitable method for calculating time-dependent deflections of pre-stressed members may be used, provided all effects are considered. Guidance may be found, and I always think this is pretty interesting, guidance may be found in ACI 209R, ACI Committee 435 from 1963, okay, from 1963, the Branson et al. Method from 1970, or the Gawley and Favre response from 1986. So it points you to some references to go look at, okay? I think what we are going to use, right, at some point I'll show you this ACI 435. I have a copy of it, and we can kind of briefly look through it and show you. But that ACI Committee 435 is the committee on on deflections. ACI Committee on Deflections. Let's see I think it's the Branson method is what we're going to use. I'm going to check my notes here. I think it's that one. I'll write that. I think we're using this one. Uh-oh. Well, you son of a god. No, it's snapping to the, I found that I was really excited about the new arrow that they have. Oh, there's not nearly enough room to write right there. You son of a bitch. You son of a bitch. But it's not even worth saying. I think we use this. That's all I want to say. All that just to say that. I think we use this. And the reason I say that is we will use method outlined in PCI design manual.
how come you couldn't have just made that text box and then snapped the arrow off of that? Wouldn't be able to-
Shut your mouth, Sean. Whenever I make comments like that, I'm really afraid that like somebody's gonna be walking by and they're gonna say something like, "Shut your mouth," and then like I'll look out and then like the dean will be like walking by looking in, or like I'll be like, and I'll just go, "Tenured bitch." That's what I'd say. I can talk to my students if I want to that way. So I apologize, Sean. Just in case they're listening to me, I still don't want to. I'm pretty sure I could be fired. Sure, there's things I could do that would get me.
They have wires in your office.
Yeah, the wires in my office.
Why do you think all of your videos get exactly one view?
Yeah, someone's watching it. Okay. So we'll get there. So what's really nice is that PCI Design Manual has like a nice example of calculating deflections, long-term deflections, and I'm pretty sure it uses that Branson et al. Method from 1970. Okay. They have in the meantime they have updated this 435 document as well from 1960. They updated it. But next time when we get to we have to talk about immediate deflections first, right? We've laid out what ACI says to do. Right, but it does, again doesn't give you much guidance. It just says calculate it with the gross section properties, calculate with your elastic modulus. Right, that's it. They haven't told us how to do it. Right, and then you get down to long term, and it just literally says you should do it. Right, you should do it, and then go see one of these other methods on how to do it. Right, but they're very open. They say you get to decide. Lots of engineering judgment. Okay. All right, so before we get there, so we're kind of going to talk about how do we calculate these deflections. As an academic, I have to talk about this as we go along, just so you can kind of see it. This is just review, deflection fundamentals. So there's always this relationship between some sort of stress or strain, moment or curvature, or force and deflection. Right? There's a relationship, and you always see curves associated with this, and they're all related to each other. They're all built off of each other. Okay, if I have a stress-strain response, right, and I stress in my material, so this is at the material level, right? If I'm looking at the material level, and I just say, hey, if I apply at material level, if I apply a load or a stress, it's gonna respond in a certain way. It's gonna have a stress-strain response. This slope right here. This slope right here, right, is E over 1, right? Its slope is E. My elastic modulus tells me that relationship between stress and strain. And then it'll go up to, and at some point, have a nonlinear response, right? If this is steel, it would go up and then, have elastic and then like this. Or if it was concrete, it would go up and do like that. But it's at the material level what the stress-strain response is. And in the elastic region, we say that that's E. Okay? If you use that same material and you come out to this level, this would be at the section level. Right? The section level. What do I mean by section level? I mean, right? It'd be like, I don't think it does mean, it'd be like an I-beam. Right? My section level could be like an I-beam. It could be a rectangular section, right, that has steel in it. Okay, it's just something like that. If I have these members that look like this, and what you do is you apply moments to them. Bless you. Okay, and I apply a moment to this thing. Right? How does it respond? Right? If I apply a moment, how much does it deflect when I apply the moment? This over here is if I just take, I guess I could, if I have my material like this, and then I pull on it or compress it, either way. Right? How does I take the material and I pull on it or I squish it, and then I get the stress strain response. This curvature response, the moment curvature response, is if I take a section and then I apply a moment to it. Okay, and then if it has nonlinear behavior in the materials, then you'll have nonlinear response of your moment curvature, right? And this gets even more complicated when you have steel and concrete. You got multiple elements floating around. Your steel will yield at some point, and your concrete starts crushing. But or in this case, you'd have yielding at the top and yielding at the bottom, and you'd get a behavior that would look like this. And so this is called the moment curvature response, right? And that affects how things deflect as well, right? But that's what we consider at the section level. What's this slope right here? At the material level. At the section level. Huh? That's EI. That slope is. So it's a function of the material and it's a function of the cross section that we have, right? And so you may have seen that before. EI times curvature is equal to your moment, right? You did that in mechanics of materials. Didn't you see that in advanced mechanics? That's a relationship, right? Your curvature times EI is equal to your moment. Just like, E times strain is equal to your stress, curvature times EI gives you the moment, right? That's part of the EIU prime 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 relationship is somewhere in there. There was an assumption that EI times curvature gave me moment. That's built into all of that, right? So that's what that slope is right there, okay? And then at the element level, right? This is over here would be the element level. Right? At the element level, right? What do I mean by element level? That'd be if I have, like this, roll on this side, right? Point load in the middle, or something like this, where I have a and it's going to be dependent on all sorts of stuff, right? It's going to be, so a couple things. I mean, just try to capture, when you talk about deflections, they're all associated with each other. When I get to element level, right, my element level deflections, right, that's what we're trying to predict is element. It's going to be dependent on what's my material doing when I load it up, right? How does that, it's going to be composite of that, and how does my moment curvature respond? That's going to be dependent on this over here. So how's my moment relate to my curvature? But over here, it's even more difficult because it's also going to be dependent on your end conditions, your support conditions. If I got a simple support and a point load applied in the middle, because that's going to affect what my moment is doing. If I know what my moment is doing, I know what my curvature is doing. If I know what my curvature is doing, I know what my deflections are doing. And so they're all just intertwined with each other, right? We're going to be dealing all in this region right here. This guy right here, this guy right here, and this guy right here. We're just going to deal in that section. But things get really complicated when it becomes nonlinear, right? That's beyond the scope here. But if you end up doing this for reals, you may end up actually calculating like nonlinear deflections, right? And then, but so when you get to when you get to this level, you start talking about forces and deflections, right? The force deflection response. How does it respond at that? How can I predict deflections given a force? But built into it is all this other stuff that's floating around. I would like just to touch on that again. Okay. This is just to kind of close out some of this discussion here, right? This is how you end up calculating deflections from this. If you look back in mechanics and materials textbook somewhere, or what you're doing in advanced mechanics, the curvature is actually the second derivative of your displacement calculations. Did you do that? I think you had to have started here, or did she just give you the EIU prime?
She called that slope.
Slope's just the first prime.
Is that?
Is the first prime.
Second prime
Is curvature. Is what?
Moment. Yeah.
It's not the moment. EI times that is the moment.
That's what
That's where we went.
That's you started with the EI times the second derivative was the moment. Yeah.
We just always have that
Be-
float now.
Yeah, that EI float up front. It's back to this. See, this is it. You may not have seen that. That's what this is, right? EI is the slope times that curvature gives you the moment. It's all based off of that.
To be fair, she probably went over that in the derivation.
Okay, this is good though. So the curvature by itself is just EU prime prime. The moment is EI times that. Yes.
What do you mean by curvature?
Oh.
I'm like actually serious.
Yeah. No, I agree. Now Yeah, it is. Wait, okay. It is. That's a great question. You stumped me for a second. Except for I'm a doctor. I'm a figure. It is the rate of change of the rotation. It's the derivative of the slope. It's how is the slope changing over the length of the member, right? How is the slope changing along the? Because the u prime is the slope, right? And so like when you're solving this one, your boundary condition here would be u prime of 0 would be equal to 0. It's coming out with a zero rotation right there. But curvature is how is that changing over the length? I think that's the only clean way to say it. It's just like acceleration is the rate in which velocity changes. Curvature is the rate at which their slope changes. Right? And it just so happens that is equal to the moment, right? Times EI, right? And you can go back to your mechanics of materials, and we could do it. I would love, trust me, as an academic, I would love to go back and show you where those equations came from. It's awesome. And I'm gonna do it. I'm gonna spend a few minutes on, and I'm gonna show you where that came from, where that curvature came from. It comes from, it goes, you might, I'm I don't know I need to look up the specifics, but it has to do with this. It starts out with a beam that's like, you might remember.
Oh yeah, she definitely went over that.
Oh, it got rid.
With like the row.
Yes,
Yeah.
rho is curvature.
Yeah, no,
Rho is curvature.
For sure went over that.
Yeah. Rho is the curvature, but it's good. Let's take a few minutes, right? It's and then rho is somewhere in there or something like that, and maybe. And maybe what she left out was how, or maybe what you missed was how that was curvature and how that was the second derivative of u prime, right? Or the visitive of, yeah.
More of a lack of comprehension.
Yeah. But it's good. Let's solidify this. Let's take that for those of you the rest of you in the class. You fuck yourself. But then that aren't in that class. But those of you in the class, let's close that loop, right? Let's figure that out. But it involves that, and then it's the rate of change. But we'll keep going with this next step, because then this, right, is in here is the moment, and then the moment is the derivative of the shear, and the shear is the derivative of the, and then you put it all together and you get the EIU prime thing. But we'll get to that. We'll figure that out next time. This is good. It's a good discussion, because this is just structural behavior in general. This is behind all of your deflection calculations. I think it's worth, and it's more fun than just saying, look at this prescriptive method. So we're going to do this. Okay.